Okay, more economic growth. And I'm going to remind myself where we got to. So, yeah, we did this very quick overview. What drives growth? And we found that it's technological progress. Then we started looking at neoclassical growth models. Right, and we looked at the basics. And we looked at what a production function is. Then we looked at the assumptions of the neoclassical model. Right, and then we got on to Solow and Ramsey. Solow being a special case of neoclassical. And we started with constant technology, which is very straightforward. We looked at constant elasticity substitution, and then we set up this picture, which we're going to talk about. Right, and then we got to Solow with exogenous growth in labor productivity AL. And at this point, I realize we need to do some math. Okay, so this is actually a pure maths video. Okay, for some of you this will probably be pretty tricky. For others of you it may be very straightforward. We'll see. So I'm going to jump forward to the mathematical appendix. What are we going to do? I don't know how many videos this is going to be, by the way. It might take a couple of videos. We're going to start with the chain rule, differentiation. Then we're going to look at differentiation like an economist, which will be something new to probably all of you. Then we're going to combine the chain rule and differentiating like an economist. Then we're going to look at balanced growth, so we're going to start getting into economics. Balanced growth is a concept in economics. And finally then we're going to look at differentiating with respect to time. Okay, differentiation and the chain rule. Okay, look, how can we differentiate x squared cubed? Well, x squared cubed is x times x times x times x times x times x, that's x to the sixth. So we could just say, well, that's 6x to the fifth. But we could also use something called the chain rule, which is that we first differentiate the outside, treating the inside as constant, and then multiply it by the differential of the inside. So then we could say dy dx is 3. So I'm going to start taking note, helping you here. So we've got like the inside cubed. So then when we differentiate that, we get 3 times that squared. Okay, so that's 3 x squared squared. But then we go to the inside, which was x squared, and differentiate that, and we get 2x. And according to the chain rule, the overall result will be 3 times 2x. Sorry, 3 times x squared squared times 2x, which is 6, x to the fourth, x to the fifth. Okay? I'm just trying to convince you that the chain rule actually works. Second case, y is 2x plus 1 cubed. Now, we could work that through. We could work out this cubic thing and get terms in x cubed, x squared, x, and plus 1. It would be like 8x cubed plus whatever x squared plus whatever x plus 1. We could differentiate that. Or we could just use the chain rule and say that dy dx is 3 times this squared, and then go inside and differentiate the inside times 2, so it's 6 times that squared. Okay, So that's the chain rule. Very, very straightforward. Most of you probably quite happy with that, I hope. But if not, no matter. You'll soon get the hang of it. Okay, what about differentiating like an economist? Well, imagine we have this following expression, y equals a whole load of stuff times x. Then we can say, well, dy dx is that same whole load of stuff. Full stop. Right? Because when we differentiate with respect to x, that x turns to 1. But we could also just say, well, actually, y is blah, blah, blah times x. We could also just say that dy dx is the whole thing, which is just y, divided by x. Because y over x is this stuff, right? That's a whole lot easier. Okay. And what if it was, now this isn't in the notes, what if we had y equals x squared? Or this whole lot of stuff times x squared? If we were going to differentiate like an economist, what would we get then? Well, we have 2 times everything divided by x, don't we? So in that case, it would be 2y over x. Okay. And if it was x cubed, we would have 3y over x. Okay. Because then it would be 3 times all this times x squared, which is 3y over x. Very straightforward. Okay. And why do I call this differentiating like an economist? Because economists are often interested in elasticities. And elasticity in this case would be dy dx times x over y, which when we differentiate in this way, we can see straight away it's just 3. And all this stuff makes no difference here. So why would we need to write it down over and over again? This way it takes us much more directly to the answer we're looking for. Okay. So I would strongly recommend you to get used to the idea of differentiating like an economist. It's quicker and it's safer. Okay, because you're much less likely to make mistakes. This way, because you're not writing a whole load of stuff out, which you can end up writing errors. Okay. That is differentiating like an economist. That is my name for it, right? I've never heard anyone else use that, so don't expect to find that anywhere else. Okay, what about combining the chain rule and differentiating like an economist? So, what if we've got y equals gamma x1 to the epsilon. That is epsilon, right? Y equals gamma x1 to the epsilon plus 1 minus gamma x2 to the epsilon, all to the 1 over epsilon. As many of you know, or some of you I'm sure, this is what we call a CES function here. Constant elasticity of substitution. Okay, so what if we're going to differentiate this with respect to x1? Oh, there's a typo there, isn't there? It says dy dx. It should say dy dx1. dy dx1. Well, the chain rule tells us it's 1 over epsilon times this to the 1 over epsilon minus 1. I'm just going to put a dot there to represent that, to the 1 over epsilon minus 1. And then we need to go inside and differentiate with respect to x1. So we get epsilon gamma x1 to the epsilon minus 1. That and that go out, don't they? But also, 1 over epsilon minus 1 is 1 minus epsilon over epsilon. Times gamma x1 to the epsilon minus 1. But this is starting to look very similar to this, isn't it? The only difference is it's this raised to the power of 1 minus epsilon. So this bit is actually y to the 1 minus epsilon. Times gamma times x1 to the epsilon minus 1. But I'm going to write it gamma x1 to the epsilon, which is what we had inside, divided by x1. So that's the minus 1, isn't it? Okay. And this actually looks very much like the result of differentiating like an economist, doesn't it? If we think, 1 over epsilon times what we started, but subtracting 1 from this, then we have 1 over epsilon minus 1. And if we can manage this in our heads, then we can think, 1 over epsilon minus 1, that's the same as 1 minus epsilon over epsilon. And thus we have y to the 1 minus epsilon. And then when we go inside, we can see, this 1 over epsilon is going to cancel with that epsilon. So we don't need to write those out. So we've just got y to the 1 minus epsilon. And then going inside, epsilon, which we've already cancelled out, gamma x1 to the epsilon over x1. Okay. So we're going to do quite a bit of differentiating the CES in this course. So hopefully you'll get to the state where you can actually confidently write this down. But if you're not confident, write out the steps. Okay. You should only do this kind of shortcut when it feels more or less automatic. That you can just see how you come straight from here to here. If you can't see that, do the steps. Okay? Right. I think I'm going to stop this video and then we'll do the second math video on growth and time. Okay, so let's see if I can stop it.